Alrighty, so just to kind of do the repetition here, not just because of the recording, but because by the time we get to the test, we'll have 3 different conics we have to look for. Parabolas, only x squared or y squared, not both. Can't be both. With ellipses, you need x squared and y squared, and you must have a plus in between those two. With hyperbolas, we'll have x squared and y squared, but we're going to need subtraction between the two. So I look at this, and even if all the blah, blah, blah weren't there, I see there's an x squared and a y squared. So at the end of the chapter, there would be a possibility that this was either an ellipse or a hyperbola. Now, figuring the rest of this out will come during the process of completing the square. Because what we want to do with an ellipse is make it look like this. Or in the case of a vertical ellipse, you know, the A and the B will switch positions down there. But that's what we want it to look like. And having binomials squared is what we do when we complete the square. So I start thinking, well, that will mean I need all the x stuff together in one spot if I'm going to complete the square for x squared. And then I'll need all the y stuff in one spot to do that. So let me get all of my x business together here in the front, and then my y squared business and the y in the back. And that leaves me with what to do with the number. Well, I'm going to complete the square, and that number's in the way. So I'll just move it over to the other side for now and see what happens. All right. When you complete the square, you have to have a 1 in front of your squared term. So normally what we would do, I mean, this is, I know Mr. Bloom and Mrs. Peterson teach this a little bit differently. Normally what we do is say, well, let's divide this 9 out of here. Let's move it over to the other side. We can always move it back later. But if we do that, then we're going to have a really nasty 25/9 for this one. So instead of moving them over, we're just going to pull them out of the way for a minute. And we're going to say both of these are divisible by 9. So let's do that. And let's just leave it sit there and we'll think about what it's going to do. And back here, a 25 could be pulled out of these two. Like so. But by doing that, we have to always be thinking, whatever I add to this side, I have to remember it would need to be multiplied by 9. Because whatever I do over here, I have to do over on the right-hand side. That's algebra. What you do to one side, you have to do to the other. And whatever I figure out to use for completing the square in this position really is being multiplied by 25. And whatever I get, I have to add on the other side. So, it is still as easy as b over 2 squared. But there's a little extra thinking because of these numbers out front. So now, here's my b. -4. I divide it by 2, and I get -2. I square it, and I get 4. And I ask myself, did I really just add 4 to this side? I didn't. Because remember, this 9 was waiting out here. We really just added 36 to this side. If we distribute that, what I do over here, I have to do over here. Those are the rules of algebra. Keep it balanced. Well, then I go after my y's. Oh, that's a nice number. 2. 2 divided by 2 is 1. 1 squared is 1. Hey, I just added 1 to this side. Nope. 25 times 1. I really added 25 over there. Now, why did I do that? Because I wanted to see that this was a binomial squared. This is x minus 2 squared. And I wanted to see that this is really a binomial square. And I don't have a horrible number over on the other side, do I? What's over there? 225. But it's supposed to be 1. I mean, that's ellipses and hyperbolas, by the way. We need a 1 over there. So what did we do before if we needed to have a 1 over there? Divide everything by that 225. So we're going to take each of these terms and divide them by 225. that's all because we want a 1 right over there. That's what we want. 9 over 225. What does that reduce to? Yeah. So that's going to look like, oh, well, that'll be perfect. X minus 2 squared over 25. Cool. That's what we need it to look like. Plus, and again, now we know this is an ellipse because we see the plus when we set this all up. Oh, wait a second. So we just did the math for this one too, didn't we? If 9 goes into 225 25 times, well then this must go in 9 times. That happens a lot with ellipses. That repetition. Right?
Yeah, that does.
It happens a lot. Alrighty, so now what they wanted was based on what we found right here. They wanted to know where the vertices and the foci are at, but that depends on where your center is. So we better figure out what the center is of this one. Where is the center? 2, -1. Good. H and K. 2, -1. Is this horizontal or is this vertical? How do you know it's horizontal? What are you looking for? Yeah, the bigger number is under the X, so this is horizontal. So, mostly people do this in their head, but you could certainly do this to get the drawing in your head and say, okay, I've got this 2, -1, so right there is going to be my center, and this is going to be horizontal, so 2, -1. So when I put my focus and my vertices on there, the -1 is going to stay where it is. But because it's horizontal, I'm going to be moving this way. So I'll have to add and subtract whatever I need there. Okay. For the vertices, there's another number that's important. What's that number? The 25, exactly, because that gives us A. So what is A? A is 5. And if you need to, you go to your drawing and you say, all right, I have to go 5 that away. 5 that away, and do the math and figure out, well, 2 minus 5 would be -3, -1. And 2 plus 5 would be 7, -1. So I'm going to put big V. They typically don't ask, this book doesn't ask for the full vertices. A lot of other books do, so we would use the V value to find those, but this one just wants the foci. So I think we can produce the name. Do you remember the formula to use if we're missing the foci? C squared equals A squared minus B squared. That's the really important part there, is that because the formula itself has addition in it for an ellipse. To find something that's missing, you have to do subtraction. Oh, well, we already have A squared and B squared right here. 25 minus 9 is 16. Well, then, C is plus or minus 4. Now, is that going to be on the same horizontal axis, or does that go the other way, vertical? Horizontal? Yeah, always on the major axis. So, instead of adding and subtracting 5, you just need to add and subtract 4. And I'll put a big F there. Okay. There and there. 2 minus 4 would be -2. -1, because they all still lie on that horizontal axis there. And then we have 2 plus 4, which would be 6 -1. Or you can just kind of think, well, they're going to be one inside these. And they have to be inside. When you're talking about ellipses, those foci are always inside the ellipse. Oh, we're still using all the concepts that come with ellipses so that no matter what they ask us to do, we can just kind of work our way through it. Even just a basic sketch, really basic sketch. So that means we shouldn't be all scared of word problems with this stuff. It's not bad. Because of their shape, ellipses are used to make reflectors of sound, light, and other waves. If we rotate an ellipse in 3-dimensional space about its focal axis, the ellipse sweeps out an ellipsoid of revolution. Looks a lot like a perfect egg, a very perfect egg. If we place a signal source at one focus of the reflective ellipsoid, the signal is used to make mirrors for optical equipment and to study aircraft noise in wind tunnels and to spy. I had mentioned this before. There are places that are called whispering galleries. When they first figured out what this did, way back when, George Washington times, they would try to get whoever it was they wanted to spy on to stand at one focus in the room. And then they'd have another person at the other end of the focus listening. Because truly that sound, even a whisper, can be heard at the other focus of the room if it's made elliptically. So in architecture, ceilings in the shape of an ellipsoid are used to create whispering galleries. A person whispering at one focus can be heard across the room by the person at the other focus. An ellipsoid is part of the design of the Texas State Capitol. And it says a hand clap made in the center of the main vestibule at one focus of the ellipsoid bounces off the inner elliptical dome, passes through the other focus, and bounces off the dome a second time, returns to the person as an echo. So when nobody's in there to bring any of that noise, I was just thinking about all the fumbling spy movies that I've ever seen. If you remember watching Pink Panther or anything like that, somebody over here would sneeze, and the Big Panther over here would say, "Bless you!" So they know everything was being said. But it worked. It was something that they could use in order to do spying until somebody figured out the math in another country, and then they knew what was going on. So they're still around, definitely historic. This is the ellipse at the White House lawn, and it says it's 616 feet long and 528 feet wide, and we want to know what is its equation. Well, there it is. Is it horizontal or is it vertical? How do you know it's horizontal? It's longer that way. So we're going to need x minus h squared over a squared plus y minus a squared over b squared equals 1. So what are we supposed to use for a center? I don't know about you, but I want the easiest center possible. So myself, exactly, I would set it up so it is perfectly centered at 0, 0. Makes it even a little easier. So we've got one problem. We need A and B. How do we get it? That's all you have to do. Divide by 2. That's all we have to do. So we take that, this is actually 2A value of 616, and we divide it by 2. And that gives us 308. So this will be 308 squared. And we're going to take the 528 and divide that by 2. And get 264. And that's B. Now, would anybody ever leave it that way? Probably not this one, because these numbers are things that will fit on our screen without scientific notation. But if it would cause the calculator to use scientific notation, then typically they just get left like this. But these numbers are not that large, so we would go ahead and find 308 squared and 264 squared. And yes, it looks like a monster when we're done. Where your 0, 0 is. You want to put it in the easiest spot possible. Right smack dab in the center. Then you don't have to do any counting to figure out what's going on and all that good stuff. Now, there are, besides the spying thing, medical uses for elliptical shapes. And this is one they don't do a whole lot anymore. This is for kidney stones. Generally, they just figure, people will pass kidney stones. It's what happens for most people. But some people get themselves into so much pain that they actually do try this. And usually they'll use ultrasound now. They don't necessarily use a lithotripsy anymore. Ellipsoids are used in healthcare to avoid surgery in the treatment of kidney stones. In case you've never known anybody with kidney stones, the kidney kind of isn't functioning properly because of the person's diet, and so it forms calcium deposits. Calcium deposits can actually grow into really hard rock-like substances, and that's what a kidney stone is. The whole problem is, at some point, it has to come out, and it can be very, very painful, as basically people are trying to urinate this kidney stone out. So an elliptical lithotripter emits UHF frequency shock waves from one focus, with the patient's kidney carefully positioned at the other focus. Notice, needs to be at the focus. So they have the machine at the focus. They use this elliptical shape to shoot out those waves, those UHF shock waves, and the person's kidney needs to be lined up right at the other focus, so they can try to break up those rocks in there. And that's one of the things they'll try if somebody's really experiencing a lot of pain. So example 6 says, the ellipse used to generate the ellipsoid of a lithotripter has a major axis of 12 feet and a minor axis of 5 feet. How far from the center are the foci? So where are you going to put those foci? Well, let's see. So I start thinking, must have something to do with c squared equals a squared plus b squared, minus b squared, because we need the foci. So let's see. Do we know a, or could we find this pretty easily? What's a? 12 divided by 2. Oh, we can square that. That's 36. Do we have b, or can we find b pretty quick? What is it? 2.5. Now 2.5 squared, grab a calculator if you need to, 6.25. Now it's a word problem. So that means we want a calculator answer, and we're going to see what we get as a decimal, and hopefully it's not something awful. If it is, we'll see what we can do with it. So we've got 36 minus that 2.5 squared. And then we have to take the square root. And because we're going to be describing a distance here, we're not going to worry about plus or minus. So 5.454. Now, it's possible we could do something to help that out a little bit, depending on what the label for that is. What's the label for that? Yeah, this is in feet. Now, they want to be pretty careful about where they put this. So they probably don't want to keep this in feet. They probably want to do 5 feet blank inches, so that they can figure it out. In fact, most of the time, they're going to be using metric to try to get this super close. So C equals 5 feet. And we would just subtract away the 5 here, because we don't need the 5 feet, and multiply that times 12. So about 5.452 inches. Now, it wouldn't have to be exact, because they can tell the patient, move just a little bit this way, move a little bit that way. And typically that person will have some pain meds in them at the time, so they can't feel the kidney stone actually being broken up. But yeah, I have heard, I actually haven't known anybody in my family that's ever had kidney stones, but I've had neighbors that have had them before, and they said this is not good. So anything to get rid of the pain. This one. The moon travels about the Earth in an elliptical orbit with the Earth at one focus. Yeah, it's not a perfect circle. It's not. It says the major axis has a length of, and we can see it in the picture here. I don't really like the placement of it because it kind of makes it look like it's just there to there. But this whole thing is 768,806 kilometers. And the minor axis, the whole thing, 767,746 kilometers. Here's what we want. Find the greatest and least distances from the Earth's center to the moon's center. Okay. Earth's center. Here's the moon. All right. So we have to visualize the moon going around and think, where will it be the greatest distance from Earth? Can you see it? That's where it's going to be the greatest distance from Earth. So I think, okay, well, I can find half of 768,806. I can get that. Let's see. 768,806 divided by 2. All right. So this is really 3,844,003. Okay. But I'm missing this little chunk. Now that must be something we're supposed to know so that we can find it. The moon travels about the Earth in an elliptical orbit with the Earth at one. There it is. Focus. It's at focus. So this distance from the center to the Earth is c. And if we can find that, we can just add it to the 384,400. And we'll have it. Well, let's see. It's an ellipse, so c squared is going to equal a squared minus b squared. We just found a. C squared equals 3,844,003. Oh, that doesn't even look recognizable. Can we get b? How do we get it? Divide the other one by 2. Exactly. That minor excess by 2. 767,746 divided by 2. Make sure I press that in right. There we go. So this one is 383,873. Whew, those are some whopper numbers. So let's see what happens. We have 3,844,003 squared minus 3,838,73 squared. Square root of that really obnoxious answer. There's C. What are we going to do with it again? Yeah, we got to add that to this 3,844,003 so we can see where that greatest distance is. So greatest distance. Oh wow, that's greatest. That's better spelling. Distance. Oh, smart person, I keep it up. Looks like this. So we have 3,844,003 plus 20,178.857. That'll be our greatest distance. And there it is. $404,581.857 what? Kilometers. Whew, that took a little bit. We're not done. That was the greatest distance. Can you see where the least distance will be? Where would the moon need to be lined up for that to be the least distance possible? So still on the horizontal thing here? Horizontal axis? Right there? Yeah, that's where it's going to be. Boy, I hope that doesn't take a lot of new math. Does that take a lot of new math? Why? Oh, just subtract. Yeah. All the way across here, 3,844,003. And subtract our 20,178.857. Least distance. 364,224.143. Kilometers. Now, is there anybody that's questioning that that would be the least distance? Because if there is, we can go through and do more math to try to figure out, is there a shorter distance? Okay, because I was working through that ahead of time. Every once in a while, there's somebody that's convinced that right here would be the best spot. And that just takes the Pythagorean theorem to prove it wrong. It's not going to work. It is not shorter than, and you learn in geometry, the shortest distance is a straight line, perpendicular from the point that you're starting at. So there it is. Well, those were word problems, and we talked a little bit about the uses. So this was totally application. We also had that completing the square one. So while you 4, 3, 2, 0, let's do this in two steps. The completing the square problem. 4, 3, 2, 1, 0 me on completing the square to prove that it's in this. A little rusty with completing the square, huh? Yeah, a little bit. We'll get there as we practice that group this week. 4, 3, 2, 1, 0 me on the word problems. Even though they're word problems, I see you're saying we had pictures. That was pretty helpful. Okay. Looks good. Looks good. So, get this one up here again. And we have work time. We are only going to do the first 3 sections of chapter 8. And then we're taking a day and a half review, and then taking a test. And then we'll do 6.1 and part of 6.2. Have a little review, take a test, and then work on the final. And we didn't have our meeting yet about what they chose for finals day.
How do we have a day that now? Like 30 minutes of review and then test 30 minutes?
No, what's going to happen is we're going to put the review for the final for chapter 8 in there as well. So it'll be review for the test, actually 2 full days, but part of it will be multiple choice because we want you to get used to what these would look like in a multiple choice format for the final. So we'll put both of those in there, and that'll get you even more prepared for the chapter 8 test. But really, I don't think we needed 2 days. I mean, that was my argument when we were sitting there. Really, do we need 2 days for times? But it'll be good to see it in multiple choice format for the final as well. All right. Well, you hit the lights here so you can see all of your stuff.